Yeah, good morning, Shubham Jane. Last two classes, electric flux and Gauss law, we have discussed in detail. Now let us make use of the Gauss law in finding electric field intensities. Remember, I have told you that we have introducing Gauss law as a tool. Now the most important point is that Gauss law can be applied for both discrete charges or system of discrete charges, and even for distribution of charge, that is whether it is continuous distribution or non-uniform distribution, uniform distribution. For all such cases it is applicable. Now this application of Gauss law in finding intensity of electric field is a three-step process. Now first let me write those steps 1, 2 and 3, and we should immediately make use of those three steps and start finding the intensities. Now step 1 for Gauss law application is construction of Gaussian surface. This we have explained in the earlier classes. Gaussian surface, right? A closed 3D, right? A closed surface, a 3D geometry enclosing the given charge or the given system of charges whatsoever. And we have explained even the properties of the Gaussian surfaces. It can be both symmetric and as well as asymmetric, but rather we always take it as a symmetry for our mathematical convenience. So step 1, construction of Gaussian surface. Step 2, very interesting, you see, very interesting. It's a step process, as I have told you. Step 2 is, once we construct the Gaussian surface, you divide the Gaussian surfaces. You divide the Gaussian surface into large number of small elements. This is English part. Now when we consider a Gaussian surface, that Gaussian surface may contain either only one single type of surfaces or multiple types of surfaces also. When I tell you this, it looks a bit, it doesn't convey a picture, but when actually we start doing that, you will come to know, you see. So what is step 2? Step 2 is divide, yes, the Gaussian surface, I call it GS, the Gaussian surface, into, yes, large number of small elements. Now the step 3. Step 3 is consider one such element. Consider one element. When the question comes, consider one element, this is where that I have told you earlier. There can be one type of element of surface or two types of elements of surface. It all depends upon the type of Gaussian surface that we have constructed. So consider one element and apply Gauss law. Apply Gauss's law. Right? Apply Gauss's law. Now in step 4, what we do is that we evaluate the integral, the calculus part. That's a simple thing, leave that aside. So there is step 4 as well. What is the step 4? Yes, after we write this step 3 for an element of surface, in the step 4, we will consider due to the total surface, that is we add all those elements, and that is what is the simple calculus part, integration part we will do. Now, let us begin with the simplest case of applying this Gauss law, right? Now, earlier we have told the distribution of charges when it was there, continuous distribution, we have taken the linear charges, the surface charges, is it not? Now let me begin with the simplest of the cases, that is linear charge. Now, I hope you are ready with this step process. Step 1, 2, 3, and of course the fourth one is a simple calculus part. Right. Now let us see It sounds simpler, is it not? Step 1, step 2, step 3. In fact, let us see when we start using these steps, whether it is simpler or complex. Let us see. Now the question comes, so these are what we call derivations. Derivations, confusions and many other things a teacher keeps listening from the students. But as I have told you, the derivations are the simplest things for our examinations. Because not a big memory, simple logic. Now let us see the derivation part. Very important question for board examination as well. This one. What is that? Long line of charge. Long line of charge is our topic. And we are now finding the electric field intensity. Remember, here we said it is long line of charge, or else we should also say line of charge of infinite length. Here the length is not finite. Now what do we mean by such long or infinite, not finite length? Let us see this beautiful concept. I tell you, this is what now my representation, and this is what is the entire physics. After this, from this representation, you can easily make your notes, derivations. Right. Now here I show a long essay. Therefore here, this is a Y. And look here, I have made it as a dotted line. Means I don't know where the ends are. It's too long, not a finite length. And supposing it is charged, and that charge I show with this blue color, suppose it is positively charged. Even it can be negatively charged as well, right? So this is a positively charged long wire such that its linear charge density is lambda, right? So what is that lambda here? The charge per unit length of the wire. And here comes a point P. This is a point P at which we are interested to find the intensity of the electric field. And let me take this point P, and the distance from this linear charge is small r. So small r is distance of the point of observation. P is the point of observation. Right. Now what we do? Step 1. First for step 1, you construct Gaussian surface, right? Right. Now you see, again I am using this blue color. Now here, this is what is with the dotted line I am writing. The same here also as a symmetry. This is this is, can you find the shape of the geometry? Yes, this is what is a cylindrical enclosure. A cylindrical enclosure. I would like to show you like this, right? So now supposing if you do it completely like this as a cylinder, if this is what is a cylinder, where is this cylinder now, you imagine? Yes, this is the cylinder, the Gaussian surface that encloses a linear charge like this. You imagine this as a linear charge, and this is what is that you observe. The same is the figure here. In fact, I have given a much magnified one as well, right? So this is the Gaussian surface, which is in the form of a cylinder, enclosing this charged wire or this long line of charge whose linear charge density is lambda. Now the question comes, so what is the length and how much length? This is all our choice. Now I will take, this is a cylinder of length L. This is a cylinder of length L and radius R. Supposing it is a cylinder whose length is L and radius is R. So for such Gaussian surface, now we will use the step 1, 2, 3. Now every time I tell you, please write notes on your own. It's a very simple thing for you right now. What is that? Let us consider a long line of charge with a linear charge density lambda, charge per unit length. P is a point at a distance r from the line of charge. To find the intensity at P, let us assume a Gaussian surface which is a cylinder of length L and radius R, enclosing the line of charge which is at the center. So this is what is the notes making. This kind of simple notes making should be your job, you see. Not any longer you can just go on, depend on others for such very smaller things also. Now, see, I have shown you this is what is the Gaussian surface. Now, when you look at this Gaussian surface, you will find two types of surfaces, I said. What are those two types of surfaces? See, this is what is one cylindrical cylinder. When you consider, this is one curved surface. This is the curved surface, and this is one type of surface. And what is the second type one? This is what is the flat ends, which are planar. So this is a planar surface of one end. This is a planar surface of the other end. So planar surface, one type of, and the other type is the curved surfaces. So here the Gaussian surface has two types of elements of surface, right? Therefore now what we will do is that apply Gauss law for each type of surface. Now let us see. Now here, as earlier I have told you, this is an element I will consider on the curved surface, So this is one such element of area ds bar. Remember, ds bar is always normal to the surface. So this is what is, yes, ds bar, the areal vector, ds1 bar I will write. And one more type of element of the surface we will have is planar. ds1 is curve 1. And look at this one more element here, I will take it on this planar, which I am representing with this red color. So this is again an outward normal. I will write this as ds2 bar. Element of planar surface and the element of curved surface. Now, the most important point is representing that electric field which is produced by this one, right? And now here, remember, this is one principle. Whenever, because even it is there in the case of flux also, we have taken E times S cos theta. What does it mean? The flux always enters or leaves the surface at right angles is a principle. Any conductor when you consider and you charge it, whatever electric field that it causes, or else in the case of even the Gaussian surface also, flux leaving or flux entering, the inward flux or outward flux, the flux always leaves or enters at normal to the surface. Therefore here I am using one more color. Let me use this as a green color. This is what is, can you see this please? Let me write it as this is ds1 bar. Now this one is, I am writing it in green color. Please find it. Whether it is legible or not, I don't know. Please zoom it and find it. So this is what is E bar. This is what is E bar. Is it not? Therefore now you see, I am now applying Gauss law. Now, for curved surface, I will write. Afterwards we will write it for planar. For curved surface, at ds1, at the element ds1, what do you observe? See this figure one more time. See this figure one more time. ds and what is this vector in the green color? This is what is E bar. Right? So what is that you observe? At the element ds1 bar parallel to E bar. Parallel to E bar. That is theta is equal to 0 degrees. Now let us write the Gauss law. Now for using Gauss law. Using Gauss law. What is Gauss law? Yes, it is integral E bar. Let us try to write it. E times ds times cos 0 degrees, because here you have the result that the ds bar and E bar parallel. E ds cos 0 is equal to, yes, it is d or q by epsilon naught. Q by epsilon naught. Now here you write, mention Q is, yes, what is Q? Q here in the RHS of your Gauss law always represents net charge enclosed by the Gaussian surface. Remember that symbol sigma Qi. Therefore here Q is net charge, yes, enclosed by the cylinder, the Gaussian surface of length L and radius R, right? Therefore now what is the value of Q? This is what we write integral. E is a constant everywhere, because this is symmetry is there, you will find. Any element on the Gaussian surface is equidistant from this line charge, which is exactly at the center of the cylinder. Is it not? Therefore E happens to be same at each and every element. Let us make mention of that also. Capital E is same in magnitude. Okay, mod E bar, let us write. Mod E bar is same at each element. Mod E bar is same at each element. Therefore we will write it this rewriting equation as E integral ds, of course this cos 0 I have taken as 1, integral ds is equal to, now how to write this Q? Earlier we said Q, the charge, linear charge density, remember Q is equal to lambda into L, where lambda is the charge per unit length. Therefore now this is enclosed by a cylinder of length L and radius R. Therefore here this Q becomes lambda times L. Is it not? This Q becomes lambda times L, charge per unit length, into length, the total charge which is enclosed. Remember, this Q is not the total charge on the line of charge. No, please remember, this is what is the charge enclosed by the Gaussian surface, which is a cylinder of length L. Is an important thing, right? Lambda times L by epsilon naught. This is for one element. This is for one element. Now we will evaluate this integral as a step 4. I am telling you, this is what it becomes a part of the step 3 only. Now integral E ds, E times, right? Yes, what is S? The surface area of cylinder. S for surface area of cylinder. Surface area of cylinder. You want me to write that? Okay. This is what is surface area of cylinder is lambda times L by epsilon naught. Now, the question comes, what is the surface area of a cylinder whose length is L and radius R? A common sense in our high schools. Therefore, now I am writing this as E times 2 pi R into L is what is the surface area of a cylinder. Remember, this is the surface area of the cylinder. Which part? I am telling you the curved part of the cylinder. Please do remember. Of course, still we have those two flat surfaces, the planar surfaces as well, which we will write afterwards. E times 2 pi R into L is equal to lambda L by epsilon naught. Is it not? Therefore, now you will mention this. E is equal to, what is that expression you got? E is equal to, yes, lambda L by 2 pi epsilon naught R. 2 pi epsilon naught R. Now this is with respect to the curved part of the Gaussian surface, right? Three-step process. Did you find it easier? Gaussian surface, yes, a cylinder, and then writing for the curved surface element ds1 parallel to E bar. Gauss law is applied, and then we have taken that small calculus. Because here, what is ds? Element of one element of curved surface. If you add, integration means nothing but continuous summation. You add all the areas, you will get the area of the curved surface, which is 2 pi R times L. This is one expression you got. Now let us come to the case of planar part, the flat surfaces of the Gaussian surface. Therefore, now for the flat surface I am writing. For the flat surface I am writing. Now here you will find that this is ds2 bar, where of course the field, as you can see, yes, this is what is E bar. Green color you find it. Green color you find it. This is what is E bar. The same way as we have represented at ds2 bar. Therefore now what happens at element ds2? What is that you find? It is not parallel. It is perpendicular. ds2 bar perpendicular to E bar. Theta, yes, 90 degrees. Theta, 90 degrees. So using Gauss law, this becomes cos 90, which is equal to 0. Which is equal to 0. What does it mean? What does it mean? The flat surface is not contributing to the flux. The flux is contributed only by the curved surface. Right? Here in this case, there are two types of surfaces for the Gaussian surface. One is plane, one is the curved part, which is contributing for the flux. But whereas the second part you will find for the flat surface, this is what is 0. That is what is our statement. The flat surface does not contribute to flux. Does not contribute, right? Flat. This is, and hence what is our final result? What is our final result? Yes. Final result is the same. E is equal to lambda L by 2 pi epsilon naught R will be the result, right? So I am now finally writing the result. The result for the long line of charge. Remember, long line of charge we have taken. No finite length here. Long line of charge. Long line of charge. We have seen the derivation part. Now, what is that you will make it into your small notebook and you practice that time and again. Periodic repetition of the concept. You need these three simple things that you have mentioned. Lambda, yes, linear charge density, linear charge density, then E is equal to, yes, what was the expression? 1 by 2 pi epsilon naught, a constant term. Sorry, here L is cancelled, right? I'm sorry, Baba. I'm sorry. 1 by 2 pi epsilon naught lambda upon R. Lambda upon R. This lambda, not wavelength, please don't say that it is wavelength, it is linear charge density, and this is the case. Now, one important point to remember, E is equal to 1 by 2 pi epsilon lambda by R, where this point is, you remember, earlier we have shown the charge, line of charge, and this is the point P, which is called lateral point, at a distance R. Therefore, when you remember an expression, each and every term, and with the right meaning, this is an expression at a lateral point. At a lateral point, of course, distance is R. At a lateral point which is at a distance R. Supposing now a case arises or your own doubt, which is rational, in fact, you should have this kind of doubt. Supposing you have taken the line of charge like this. This is what is the line of charge, right? And you have taken point P over here. Suppose this is a long line of charge. This is point P. Now where is this point P? You tell me. It is along the line of charge, right? If it is along the line of charge, P is not defined. There is a point. P is not defined. Don't say E is equal to 0. What refers here is, of course, for this point, you will write R equal to 0 and E equal to infinity. E equal to infinity means it does not mean that it has a very huge value. In fact, it is not defined. We cannot define that point. So therefore, this is a result to be remembered for lateral point, and E is not defined. E is not defined at a point along the line of charge. Along the line of charge. Of course. Now you tell me what else you can observe and you can make a mention, which will be an important thing later. In the latter part, that may be useful for our other types of examinations. So what is that observation? Many times I have told you, look at that RHS and LHS values, how you can relate them, Now, intensity versus distance. Supposing if the distance of the point changes, what happens to intensity? Such simple things to begin with. Now, E versus R. What is that you observe? E versus R. The result is. And one more time also, I'm sorry for this. This is E at a point when we have defined at a lateral point, 1 by 2 pi epsilon lambda where. What is the direction? Yes, at a lateral point, perpendicular to line charge. Direction is perpendicular to line charge. Or else, now I will make it. Let this be. One more point, that is E bar due to line of charge is, long line of charge is, yes, always directed perpendicular to line of charge. Perpendicular to line of charge. This is very important, writing the vector. Now one more time, what is the meaning of that? If this is what is the line of charge, please remember we are writing the case of long wire. Again, There may be a doubt, what about finite length? If you have such doubt, of course, you can call your teacher, speak to your teacher, get the concept and try to do it. It will be a very good exercise for you. Now at this point P, this is how you set E bar is the vector. Supposing if this is the point other side, then also how do you write? Normal. Now remember, this is positive charge, therefore I have shown this vector away. Normal and perpendicular and away. Supposing if it is a negative charge, how do you represent? Right? Because this is what is an important thing in physics. Whenever we come across the vectors, we should have 100% clarity regarding the drawing of that vector or representing that vector. If this is what is negatively charged one and this is point P, then you will write this E bar, which is towards. Now here you will find normal, this perpendicular and away from the line of charge. Here it is perpendicular and towards. Is that okay? So this is one more important take. Now, still, as again I have told you, how do we find that relation of E and R? E and R relation. E and R relation, we have seen E proportional to 1 by R for a given line of charge. Of course, E proportional to lambda. As lambda increases, decreases, E also there is a proportionate change that is there. I am now writing only for a kind of distance. This is E proportional to 1 by R. Is it not? See, what was the result in the case of point charge, you remember? Yes, point charge, you have this relation E proportional to 1 by R square relation. You remember what was the case of intensity and short dipole? In the case of short dipole, you have E proportional to 1 by R cube. Now for the line of charge, long line of charge, you have E proportional to 1 by R. E proportional to 1 by R. See, now this is what is an important thing. Because every time when we have such cases 1, 2, 3, 4, observing them with logic. That is, now, supposing it can be a kind of CP question or a NEET question. Right. What is that? Now, I show a graph. I show a graph. And there is a question based on the graph. Now, this is distance versus electric field intensity graph. And 3 graphs are shown. The first one I show with supposing black color, it's a curve. Hope it is legible for you. Hope it is legible for you. This is black one. And supposing there is one more which is I have represented with the red color. And one more I will represent with the blue color. Suppose this is what is the curve. Now look at this curve. What is the difference you find? Don't tell me red, blue and leave that color aside. What is the other difference that you find here? The slope. The slope. You see, this is less steeper. This is more steeper. Is it not? This is still more steeper. There is a difference of the slope. There is a difference of slope. Now the question comes that which of them, supposing I call them as A, B and C, which of them represents, supposing these are the 3 curves for a point charge, a line of charge and one more is a dipole. Which of them represents point charge, which of them represents that of dipole? If that is what is the question. Now what was our earlier result? E proportional to 1 by R square for point charge, 1 by R cube. All are inverse relation only with the distance, remember. But with point charge it has E proportional to 1 by R square, E proportional to 1 by R cube, short dipole, E proportional to 1 by R. Is it not? So for all such cases, we will get curves. Because this is what we have told you earlier. All nonlinear curves will get such that what is the result? E proportional to 1 by R, E proportional to 1 by R square and E proportional to 1 by R cube. All we will get is curves. such that now here you see the index. This is r rise 1, this is r rise 2, and this is r rise 3. All of them are negative inverse relations, therefore this is what is the negative slope that you got, first thing. Second thing is that look at the index. And you know that simple mathematics that more is the index, more will be the slope. When you write y proportional to x power n, y proportional to x power n, more is the value of n, more will be the slope, whether it is positive or negative. Positive means directly proportional you get, negative means inversely proportional you will get. If now, as you can see here, this is a lesser index, is only 1, and here the index is 3. Therefore, more index, more slope is our concept, is it not? We did all such things in our first PU, simple examples that we have stated. Therefore, in such case, you tell me this is steepness is maximum, therefore the C1 refers to R cube term, therefore this represents sharp dipole, this represents line of charge, and B represents point charge. Like, so this is the case of finding electric field intensity due to line of charge, long line of charge, Gauss law we have applied, surface, and afterwards important results. Practice them rigorously. Once, twice, thrice, you attend the further next sessions, you practice all these things, and even in the earlier sessions as well. And one more thing I have told you that this we have did for the case of long lateral point. Now you please, if you have any such interest, do it for finite length and what is the result. You please discuss with your teacher. Now we'll proceed further. We'll have one more example. Let us see next case of distribution of charge and finding intensity using Gauss law again. See that? See this next case of infinite sheet of charge we have taken. In that infinite sheet means two-dimensional charge distribution, right? And one more thing is that in the case of infinite sheet of charge we have taken, again two cases it arises, possible that conducting sheet of charge and the non-conducting sheet of charge. We are doing it for the case of, yes, conducting sheet of charge. Non-conducting sheet of charge, yes, with a small logic you can write that on your own, right? Infinite sheet of charge. Here I would like to show you this kind of distribution. This is what is that you have to imagine. So this is what is the sheet of charge I have taken. Again, infinite is a very big sheet I have taken. Now for this one, orientation, what is that is important. I have shown you whatever that I am showing you here. Is this held normal to the plane of our board? Such a sheet now it is represented on the board. So this is my representation of that sheet. The sheet of charge. This red is not that much visible. Please focus it, watch, give a pause, watch it carefully. Right, this is a sheet of charge. I will call this as some, suppose let me call this as A, B, C, D. And this is what I am showing the charges. Blue color, sorry, green one. Supposing this is a sheet which is a conducting sheet and charged positively. This is what is the positive charge distribution, right? And this distribution is uniform such that the surface charge density is sigma. See, this is what is the terminology that we have introduced already. Earlier we have told that lambda, surface charge linear density charge per unit length. Now surface charge density charge by area, right? So this is a charge sheet. Okay, we got it. ABCD, a uniformly charged conducting sheet with the linear surface charge density sigma. This is how you begin with your notes. ABCD, yes, it is. ABCD is a charged conducting sheet with surface charge density sigma, which is uniform. Now please again one more time I am showing you, this is what is the orientation, This is what is the plate I am considering, the sheet I am considering, which is normal to the plane of the board. Remember, this is not in the plane of the board. No, please remember. And now I consider the point. This is point P. Point P, again, which is at a distance R, where you are taking it from. If this is how we are held, this is what is the distance I am taking, right? So this orientation and picture is very important, right? Now this is what is the distance, which I call it supposing R, not from this edge. No, please remember, R is, one more time, if this is what is the sheet of charge, wherever it is placed, and this is what is the distance we have told, right? Now let me take this point P, right? This is the point under consideration, which is P. At distance R, where we are interested to find out the intensity. Now one more time, the same, we have construct Gaussian surface. Let us see what type of Gaussian surface. As I told you, let us always think of symmetry so that it makes our mathematics convenient and simpler. This is the distance R. Therefore, now what I do is, I imagine a cylinder. Now this is a cylinder. This is a cylinder. This is a cylindrical Gaussian surface. One more time, I am taking cylindrical Gaussian surface. See, need not be, it can also be any other form like a rectangular pipe, a parallel pipe. You can take that as well. I am taking for this geometry, looks good. This is the cylinder. So what type of cylinder you find it? This is a cylinder whose length is 2r, because this is cylinder which we have extended other side also. Because when we say the conducting plate, supposing if this is what is the conducting sheet, plate, if this is charged, this is also charged. That is what is the case of conducting sheet. You cannot have charge only on one side and no charge on the other side. It is not possible. It is possible, of course, with earthing and all, but without earthing, whenever we charge a conductor, it cannot reside only on one side. It will be complete distribution on either side. Now, whereas if it is the case of non-conductor, yes, that is what is the difference. If a non-conducting sheet is taken and charged, supposing if this side is charged, this portion, this surface is charged. Now, because it is a non-conductor, charge distribution won't take place. The other side, no charge distribution, like that. Now, what is the meaning of writing this? Supposing if this is what is the sheet of charge, which is charged now, you will have flux on either side, towards your right hand side and towards your left hand side. Both sides you will have the flux, and that is why what we did is, if this is what is the sheet, you will find with the Gaussian surface cylinder whose half of the cylinder is towards your right hand side, and half of the Gaussian surface, which is the cylinder, the second half of the cylinder is to your left hand side. Why we have to consider both the sides? Yes, because the flux is contributed by both parts if it is the case of conducting sheet of charge. See, this is what we need to mention if you are making a good notes, when you listen to the teacher and making notes, which is most important. Not only simply learning physics or Gauss law here. Remember, you attend the classes to improve your expression, your writing expressions, your ability to communicate. All these things you have to make use. And I request all of you one more time that never touch these Xerox copies or other guide-like materials given by the others. They will kill all your most important essential elements that is to be grown, right? And that is why make a good notes, listening to all these things. Now what is that, right? A, B, C, D is a long sheet of conducting charge with the surface charge density sigma, charge per unit area is sigma. P is a point at a distance r from the sheet at which we are now finding the intensity. Now, to find the intensity, we imagine a Gaussian surface passing through the point P. Whenever we construct Gaussian surface, that Gaussian surface should enclose the system of charges and should pass through the point of observation where intensity is found. These are the things which we have explained earlier, right? Gaussian surface should pass through the point of observation where we are finding the intensity and enclose the system of charges, right, due to which intensity arises. Now, we construct a Gaussian surface passing through the point P, which is a cylinder of length 2r. This r is now the distance, at 2r is the length of this Gaussian surface, and let us take this small, some number I will take, some small d is the radius of that cylinder. D is, yes, radius of the cylinder, or not the radius, I have taken as the distance r, and d is the radius of the cylinder. Now, these planar, now one more time we look at this Gaussian surface, the same Gaussian surface which you got earlier. Now, this is what is the Gaussian surface you got, and this is what I have kept ready to show you to have the correct picture of our geometry. If this is what is our sheet of charge, of course this is a cut with it, don't think about it, it's a continuous. Now our Gaussian surface is like this. Gaussian surface is like this, remember? Again the Gaussian surface where you have taken it as in the form of a cylinder. Cylinder has again, yes, the curved surface, a part, and also it has these planar surfaces, the flat surfaces. One more time, the same repetition of what we did in the earlier case, right? So from now here I am taking one more time. Supposing if this is what is an element I have considered, which is yes, always outward normal, which is ds1 bar, ds1 bar, which is on the curved surface. And one more element which I will consider, one more consideration is at this point, which is the flat one, where this is what is ds2 bar. Now it is the case of flux. Now this is what we write, and I would like to show it with again red color. This is ds2 bar. This is, yes, the E bar, the intensity vector, and this is what is the E bar, the intensity vector. So again, you have to consider the elements. Two types of elements are possible. So first I will write it for an element ds1 bar on the curved surface. On the ds1 bar, yes, on the curved surface. Now look at that figure. Now everything you can duplicate, is it not? What is that? ds1 bar perpendicular to E bar, which is, you can find it there. That is theta is 90 degrees between them. Therefore, integral E ds cos 90 degrees is equal to 0, cos 90 0, right? So what does it mean? Yes, curved part of Gaussian surface. Curved part of Gaussian surface, not contributing to the flux. Not contributing to the flux. Earlier we have seen that curved surface was contributing for the flux, but in this case, second case, we got curved part of Gaussian surface not contributing to the flux. Now let us see the other part. and therefore no intensity found, that is what, no flux is contributed here. Therefore now for the, is that okay for you? Now I am writing for the element ds2 bar on, yes, the flat surface. ds2 bar, here you will find it on the flat surface. Then ds2 bar, what is that you find there? Yes, parallel to E bar theta 0 degrees. Therefore here what you get, E ds cos 0 degrees equal to, yes, now you got it, cos 0 degrees is equal to Q by epsilon naught. Now one more time, how to write the value of Q. Remember, Q we said charge per unit area. Which area now we are talking about? Yes, flat surface we are now talking about. Therefore, now Q is equal to, yes, area of flat surface. Area of flat surface, yes, into area of the flat surface multiplied with sigma. So now I am writing it as, now Q is equal to sigma times, what is sigma? Charge per unit surface area into, yes, area of flat surface. Is that okay? Area of flat surface, which is, yes, sigma times, I have taken d as the radius of this part. Remember, right? This is what is the flat part that you got, and this is what is the radius small d I have taken. Therefore, this is the area becomes pi d square, where d is the radius of that flat surface, right? Pi d square becomes sigma times pi d square. Therefore, now just make a mention of that. Therefore, this is what is integral. E is same everywhere. Therefore, E times ds is equal to, yes, sigma I will do that part here. Yes, E the same on the Gaussian surface on both the, see, curved surface means, the flat means we have two surfaces, 1 and 2. Integral ds is equal to sigma times pi d squared by epsilon naught. Now what is that integral ds? You will get the total surface area of the flat part. How many flat parts are there? Pi d square, and here also one more pi d square the other side. Therefore, this is 2 times pi d squared, yes, equal to sigma into pi d squared by epsilon naught, right? Now what is that you observe? Pi d squared on either side. So final result is capital E is equal to sigma by 2 epsilon naught. Sigma by 2 epsilon. Here, two things please do remember. What is that? When you are writing this ds of which part you are writing? The flat part. Therefore, this ds, flat part means here one area, pi d square. There is other side also which is contributing to the flux because of this conducting sheet. Therefore, it is 2 pi d square without 2 pi d square, right? 2 pi d square. Therefore, E is equal to sigma by 2 epsilon naught. Again, now the question comes, what is the direction? What is the direction? And what are the other important things that we can make also? I will discuss more about this result, E equal to sigma by 2 epsilon naught, because it's already been about more than 50-55 minutes of the video. So the class, let me not extend further. You practice till this point, E is equal to sigma by 2 epsilon naught, the intensity due to long conducting sheet of charge. Results we will discuss in our next session. Good day all of you.